Hi, this is Mrs. Cahill for review of Module 11. Number 1, what is a good example of a correlation coefficient that is positive and strong? Well, a good example of a correlation coefficient that is positive and strong is 0.9. Positive and weak, our best example is 0.9. Negative and strong would be a negative 0.88, and negative and weak, negative 0.2. So you're wondering what's wrong with the two that we have left over? Well, remember, a correlation coefficient will be no smaller than -1 and no larger than +1. Question number 2, what's the solution of the system? Well, we just get to read our answers right from the graph paper. Take a second, read those ahead of me. What have you got? On the first one, we're estimating the solution to be at -1.5, 2.5. And on the second, we've got a solution of 3, -2. Question 3, describe the following. Now you'll notice on your B and C, I've got slightly different words. Make sure when you're done, all the words I have on my answers and on my questions, you have on both of yours. When the solutions are inconsistent, that means they never touch. Therefore, there is no solution. We're talking about parallel lines which have the same slope and different y-intercepts. It is important that you know all of these words go together. On B, consistent independent, that is a system in which there is one solution. We have different slopes and the y-intercept doesn't matter. It might be the same or it might be different. Remember, consistent means we touch, independent means we are separate lines, so that would be two lines that touch in one point. On part C, consistent dependent, that's when we have got infinitely many solutions. We're talking about the same line, therefore we've got the same slope and the same y-intercept. Consistent means we've got solutions. Dependent means those two lines are the same line. Question 4, solve the system using substitution. Well, you'll notice these are easy for us because in both cases we've got y alone. If I take the second equation, I know that y is exactly equal to 11x plus 5. That means wherever I see a y on the first equation, I can instead write 11x plus 5. When I do that, I suddenly have an equation with only x, and now I can solve. I will add 11x, I will subtract 11x to both sides. And when I do that, I get x minus 4 equals 5. The next step is to add 4 to both sides, and x is 9. Now that I know that x is 9, I can take that value of 9 and plug it into either equation. In this case, I've plugged it into the first equation. 12 times 9 is 108. 108 minus 4 is 104. Don't let the large numbers fool you. You can get anything for x and y. So we believe the solution to be 9, 104, and we test it by plugging it into both of the original equations. However, I have just had my y in this equation along with the x in this equation, which is the first equation. That means the one I really need to test it in now, if I'm only going to test it in one, would be the second one, the one I didn't just use. So I'll plug in my x and my y into the second equation. And 11 times 9 is 99, plus 5 is 104. I get a true statement, and that just verifies that my solution is indeed 9, 104. If I were to graph those two lines, that would be the ordered pair where the graphs would touch. Solve this system on number 5 using elimination. So I've got my two equations. They're both written in standard form. That's really set up well for elimination. I can see right now that my coefficients on x are not opposites, and for y they're not opposites. That means I need to create opposites. In this case, I'm going to try to get my y coefficient to be 10 and -10. That's what I'm choosing to do. In the first equation, to get a coefficient in front of my y of -10, I'm going to multiply every single term through by +5. When I do, I distribute my 5 to every term on both sides. I get 25x minus 10y equals 55. Now remember, on my second equation, I don't want to get a minus 10y. I need to get the opposite, which is a plus 10y. So I'm going to multiply both sides of the equation this time by a positive 2. When I distribute, I get 6x plus 10y equals 38. And you can see I do have opposites. Those equations are all set up for elimination. So let's line them up. I've got them lined up. And you can see when I do that my y's will drop out. Negative 10y plus 10y is gone. The only thing left is 25x plus 6x is 31x, and 55 plus 38 is 93. To get x alone, divide both sides by 31, and x is 3. Once I have x, getting y is easy. Plug it into either one of my original equations. I plugged it into the first equation. 5 times 3 is 15. I'm going to subtract 15 to both sides and get negative 2y equals negative 4. Now I'll divide both sides by negative 2, and y is 2. So I believe my solution is 3, 2. I can plug it into an equation and check. I should plug it into both, but if I'm only going to plug it into one equation, you choose the equation that I didn't just use, which in this case is the second equation. So when I plug in my x and y into the second equation, I get 3 times 3 plus 5 times 2 equals 19. You can see I plugged my x in and I plugged my y into the second equation and simplify. 3 times 3 is 9, 5 times 2 is 10, and 9 plus 10 is 19. So it does check out. The solution is 3, 2. Remember, if you're in doubt as to which equation you should check your solution into, check it in both. Question 6, how many solutions do the systems have? They're not asking us for what the solutions are, so we can stop as soon as we know how many solutions. Remember, 3 possibilities. We could have 1 solution, we could have no solution, or we could have infinitely many. In 6a, my first equation is already in slope-intercept form. So the easiest thing I can do is take my second equation and also get that into slope-intercept form. So I am going to subtract my 6x to both sides. When I do, I get minus 3y equals negative 6x plus 15. And now to get y alone, I'll divide every term through by negative 3. And when I do, I get y equals 2x minus 5. So here are the 2 equations I'm going to compare. My second equation, which I've rewritten in slope-intercept form, and my first one, which already was in slope-intercept form. Well, they've got the same slope and the same y-intercept. That means if I graphed them, they would be the same line. That means there are infinitely many solutions. Many. All right, on the second problem, 6b, they're both in standard form. I could try to get y alone on each of those, but I'm actually going to start the process of solve by using elimination. I can see that I've got a positive 4y here and a negative 2y. I'm awfully close to making the y's eliminate. I'll take the top equation and multiply every term through by a positive 2 so that I'll wind up with the opposite of the 4y over there. And that's just what I did. Multiply every term through by positive 2. That gives me 10x minus 4y equals negative 12. Remember, that was the top equation. Now I'm going to bring down the second equation. I've got them all lined up, and you see I'm ready for elimination. My attempt was to make the y's eliminate, and they're about to. I've got a plus 4y and a minus 4y. I know when those add up, I'm going to get 0. But look at my x's. Those are also opposites. So when I add up 10x minus 10x, I get 0. Minus 4y plus 4y, I get 0. And on the other side, I've got negative 12 plus 8, and I get a negative 4. As soon as both x and y drop out, I know I've got a strange situation. I'm not getting one solution. In this case, 0 does not equal negative 4. That's a false statement. So I know I have no solution. That's the answer to the question. Remember, these 2 lines would be inconsistent lines. They're parallel. They never touch. That's why we have no solution. All right, on part C, we're all set up to attempt elimination. I can see that on my coefficients for y, I have opposites. I've got my positive 3y. All right, there we go. I've got my positive 3y and my negative 3y, so I can try to add up those two equations and watch my y's eliminate, and they do. Careful, 4x plus 4x is 8x, and 9 plus 9 is 18. If I want to, I can try to get x alone by dividing both sides by 8, and I get that x is equal to 9 over 4, and that's fine. I don't even need to do anything with that. I know that I'm about to get one solution. One solution on part C. All right, on number 7, on your worksheet, you might need to add a y right here where I have this blue y. There was a typo. A system of two equations includes y equals negative 1/3 x plus 1/2. If the system has infinitely many solutions, can each of the following be the second equation of the system, yes or no? And we need to show our work. So I've got my first of two equations right here, and I'm trying to identify what else could be in this system. I want infinitely many solutions. Honestly, that just means I've got the same line. And if I have the same line, that means I'm looking for an equation with the same slope of negative 1/3 and the same y-intercept of positive 1/2. What I would do for each and every one of these is get them all into slope-intercept form. Well, we're lucky on A. It's already in slope-intercept form. And I can see I do have the same slope, but I do not have the same y-intercept. That's different. Those two lines are going to be parallel, and they're going to have no solution, not infinitely many, so A is not one of the lines of this system. On part B, I need to get this equation into slope-intercept form. That means I need y alone. My first step will be to subtract 2x to both sides. Next, I will divide every single term through by 6. And when I do, I get negative 1/3 x plus 1/2. And as you can see, my slope is the same as the original. My y-intercept is the same as the original. These two will have infinitely many solutions. So yes, B could be one of those equations as part of the system. On part C, let's get y alone. The first thing I would do is distribute the negative 1/3. Be careful, make sure you distribute the negative and the 1/3. When I do, I get y minus 1 equals negative 1/3 x minus 1. Now to get y alone, I need to add 1 to both sides. And I get that y equals negative 1/3 x plus 1. Once again, we see we have the same slope and the same y-intercept as in the question. So I know that I do have the same line with infinitely many solutions. So yes, C could also be part of the system. On part D, let's once again get y alone. I would subtract 3 to both sides. Y isn't quite alone yet. I need to divide every term through by negative 1. And I see that y equals positive 3x minus 6. My slope is not the same. My y-intercept is not the same. D cannot be part of the system with infinitely many solutions. In fact, in part D, what we have is one solution if it's part of the y equals negative 1/3 x plus 1/2 from the original question. All right, question number 8. Jonathan spent $17.25 on candy bars and fruit snacks for a party. He bought a total of 27 items. Candy bars cost 75 cents each and fruit snacks cost 50 cents each. Write and solve a system of equations to find out how many of each item Jonathan bought and show your work. Well, the first thing we should identify are our variables. We could call our number of candy bars X and our number of fruit snacks Y. I actually did that already. And I'm set to write my equations. One equation can take into account the price of each item and how much money I've spent. Oh, but my first equation happens to be about my quantity of items. All of my candy bars, X, plus all of my fruit snacks, Y, add up to 27 items in total. That's typically the equation most kids struggle to come up with. I have a feeling on the second equation you could write that one yourself. Candy bars cost 75 cents each, plus fruit snacks cost 50 cents each, and all of that is a $17.25 that Jonathan spent. So I've got my two equations. I could solve using elimination or substitution. I know the book would prefer that we solve this with substitution, but I didn't use substitution. I love elimination. So what I'd like to do is get opposite coefficients. There's a positive 0.50y here. So I'd like to get a negative 0.50y here. To do that, I'll multiply every term through in the first equation by negative 0.50. Be sure to distribute that to every term. And when you do, you get negative 0.5x plus negative 0.5y equals negative 1350. Now I can line up my two equations. I'm going to bring down the green one and line it up. And you can see my y's are about to eliminate because they are each opposite. Negative 0.50 plus positive 0.50 is 0. Adding up my x's, I've got a 0.25x. Adding up my money, I've got $3.75. Now I'll divide both sides by 0.25, and x equals 15. And remember, x was our number of candy bars, so that's 15 candy bars. Well, if I go back to my initial quantity equation, I know that candy bars plus fruit snacks add up to 27. So if I've already got 15 candy bars, I must have 12 fruit snacks. All right, when you think you know your y and your x, you plug them into the equation you didn't just use. We just used our quantity equation, so let's use the equation that takes into account the cost of each. We plug in our x and our y into the second equation, simplify, and we discover that we've got our $17.25. So our solution really is 15 candy bars and 12 fruit snacks. All right, question number 9. This is a review from chapter 4. Given the line of fit and the data, find the sum of the squared residual. So they want us to find r squared. That. Look at all the work I've got set up. You had this originally. See this table right here? I've copied that table in the horizontal form in my chart. And I've got my actual x and my actual y as given by the table. Now I'm going to calculate the predicted value for y by taking each value for x and plugging it in one at a time. And I've got that set up for you already. Can you see I plugged in my actual x into my equation and I simplified and I got a 0.5. So this is my predicted y that I got using my equation. This was my actual y. To get my residual, I subtract my actual minus my predicted, so 0 minus 0.5 is a negative 0.5. When I square that for my r squared, negative 0.5 times negative 0.5 is a positive 0.25. Now let's do it for the next one. I take my actual x and I plug it into my equation. When I plug that in and simplify, I get a negative 0.5. That's my predicted value for y. Let's compare it to my actual value for y. We're going to subtract negative 1 minus minus 0.5. So that's really negative 1 plus 0.5, which is a value of negative 0.5. I'll walk through one more with you. Oh, by the way, that's our r. Our r squared will again be 0.25. Let's do one last one with you. I take my value for x that I actually got, plug it into my equation. Negative 1/2 times 0 is 0, minus 2 is negative 2. So this is my predicted value for y. When I compare it to my actual value for y, I see that the difference is 0, and 0 squared is 0. So do the same for each one of these other values of x, plug them in, and get your predicted values for y, and subtract your actual y minus your predicted y, get your residual, and square it. You take all of your residual squareds, you add them up, and you get 7.75 as your residual squared sum. All right, question number 10, they want us to graph and solve. On our previous problems, we used algebra to find that one solution of x and y. On this time, we're going to graph. Well, the first one is nice and already set up for us. I see my y-intercept, and I see my slope. So let's begin by graphing our y-intercept of negative 3. And our slope of 1/3 means I will rise 1 and run forward 1, 2, 3. I could also fall 1 and run backward 1, 2, 3. So that is the graph of y equals 1/3 x minus 3. Let's connect those. Okay, now for the next line, it's not in slope-intercept form, and I prefer it that way. So in this case, if I get y alone, I'll be subtracting x to both sides. And when I do, I get y is equal to negative x plus 1. I see that my y-intercept in this case is a 1, and my slope is a negative 1. Remember, there's an understood 1 there. So it's a slope of negative 1. Let's graph our y-intercept of 1. A slope of negative 1 means I fall 1 and run forward 1. And I can do that multiple times. Now let's graph that line. And I can see that the solution to this system of equations is at the ordered pair 3, negative 2. If you're doing this on a test, just to be safe, I would take this solution and plug it into both of the equations to make sure that you've done this properly. All right, let's look at the next equations we're supposed to graph. The first one, again, is in slope-intercept form already. We've got a y-intercept of 2 and a slope of negative 2. So let's make sure this line is looking downhill when we're done. A y-intercept of 2 and a slope of negative 2. So fall 1, 2, run forward 1. Fall 1, 2, run forward 1. I could also rise 2 and run backward 1. And I'm set to graph that line. All right, let's graph the second line. But first, I'd like to get that second line into slope-intercept form, so I will subtract 2x. Do you notice that these two lines have the same slope, but they have different y-intercepts? Now we've got a y-intercept down here at negative 2, but we still have a slope of negative 2. That means I will still fall 1, 2, and run forward 1. I could also rise 1, 2, and run forward 1. Remember, when systems have the same slope but different y-intercepts, they're going to be parallel, and these two lines will never touch. Therefore, there is no solution. All right, on part C, we are all set to graph those as well. Let's graph our y-intercept on the first equation down at negative 4. We've got a slope of positive 1/4. I will rise 1 and run forward 1, 2, 3, 4. I could also fall 1 and run backward 4. I can graph that line. Let's graph the second line, but before we do, to get y alone, I would subtract x to both sides. Then I'll divide every term through by positive 2, and I get that y is equal to negative 1/2 x minus 1. So this time we can see that we have got a y-intercept of -1. Our slope is -1/2. That means I can fall 1 and run forward 2, fall 1 and run forward 2 again. And I will graph my line. And I've got a solution this time at 4, -3. Remember, you should take your solution of x and y and plug them in to each of the equations to confirm that our solution is indeed 4, -3. On number 11, we're going to solve using substitution. We're lucky again. They've got these both written into slope-intercept form. I know that y is exactly equal to 3x plus 1. So any place else I see a y, like right here, guess what I can write? 3x plus 1. So that's what I'll do. In place of that y, I will write 3x plus 1. And actually, I did just the opposite, but it's the same thing. I know that 3x minus 5 equals 3x plus 1, because I've just substituted the y's. So now I'm going to subtract 3x to both sides. Oh, and look, the x has dropped out. I no longer have an x or a y, and I've got this false statement that -5 equals +1. The fact that x and y both dropped out means I've got an interesting situation of either no solution or infinitely many solutions, but because it's a false statement, -5 doesn't equal -1, I know I've got no solution. And by the way, those lines are parallel. All right, on number 12, solve using elimination. We're lucky this time. The y coefficients are opposites. I've got a +5 and a -5. We're set to add those two up. When we do, -4x plus 6x is 2x. The y's do indeed eliminate. -5y plus 5y is gone. And 12 plus 2 is 14. Divide both sides by 2, and we see that x is 7. Now that we've got our value of 7 for x, we can plug it into either equation. I chose the first, and I've got -4 times 7 minus 5y equals 12. We simplify. That's a -28. I'll add 28 to both sides in my attempt to get y alone. -5y equals 40. Divide both sides through by -5, and I've got a y value of -8. So now that I've got my y and my x, I can take both of those and plug them into the equation that I didn't just use. Simplify, and we get -42 minus 40 equals 2. 2 equals 2, so I know that my solution is indeed 7, -8. On number 12, which method would you use to solve the system and why? Well, on number 12, I would use elimination. And that's because I don't have a coefficient on any of my x's or any of my y's of a 1 or a -1, which just means to isolate x or y wouldn't be any fun. These are set up for elimination. I do notice that I can find the least common multiple for 6 and 9. I'm like an 18, but remember, I do want one of those 18s to be positive and one to be negative. So I chose to take the first equation and multiply through by +3, because I know that 3 times 6 will get me my 18. If I'm going for +18 here, notice I got my +18 and I distributed to every term. But if I'm going for +18 right here, you know I need to get a -18 where I've got my 9. So I'm going to need to multiply by -2 to every single term. Distribute that -2, and we do indeed get our -18x plus 14y equals -30. Now that I've got my two equations and my opposites, I'm set to line them up, and I know my x's will eliminate. +18x minus 18x, it eliminates. My y's simplify nicely too. -15y plus 14y is -y. 27 minus 30 is -3. If -y equals -3, I could divide both sides by -1, and I know that y equals 3. Once I know my y, I can plug it into either one of my equations and solve for x. I chose the first equation, plugged in my y, simplify, that will give me a -15, add 15 to both sides. 6x equals 24. Divide both sides by 6, and x equals 4. So I'm pretty sure that my solution is x equals 4, y equals 3, but I should check. I should check in one of my originals. I just used this one, so if I'm only going to check in one equation, I better check it in that second one there, and that's what I did. 9 times 4 is 36. Negative 7 times 3 is negative 21, and their difference is 15. So it does check out. Our final solution is 4, 3. Remember, if you're in doubt as to which equation you should check your solution into, take 10 seconds and plug it into both. Number 13, adult tickets to the school play are $12 each and student tickets are $5 each. The school sold 113 tickets and made $1,132. They want us to write a system of equations for this situation, and what I should have added in this question was write the system of equation that shows us how many adult tickets were sold and how many student tickets were sold. So on my step 1, I wrote my quantity equation. How many adult tickets plus how many student tickets, and that better add up to a total of 113. Well, why don't we call our adult ticket number of adult tickets will be X, and our student tickets we'll call Y. In this case, I know that all of my adult tickets plus all of my student tickets better add up to $113. All right, my second equation takes into account the cost or the price of each ticket. $12 times my number of adult tickets plus $5 times my number of student tickets better add up to the $1,132 that were earned at the performance. These equations are set up great for elimination, and I think that's what I did this time. I did. No, excuse me, not elimination, substitution, and that is indeed what they're set up best for. All I did was isolate my y. To get y alone, I needed to subtract x to both sides, and that's what I did. Now I know that wherever I have a y, instead, I could write 113 minus x. So you see this y right here? In place of that y, I could write, with parentheses, 113 minus x. And that's what I did. So now this 5 will need to be distributed. And when you do, this is what we get. Now we can collect like terms. I've got a plus 12x and a minus 5x. Those combine to be a 7x. And now we can subtract 565 to both sides. And now divide both sides by 7. And x is 81 adult tickets. Now that I know my quantity of adult tickets, I can plug it into my first equation and find out how many student tickets I've got. So 81 plus some number of student tickets better add up to 113. The missing value, 32 student tickets. I've got my number of student, my number of adult. Let's plug it into the second equation, the one we didn't just use. Plug in the 81 for x, the 32 for y, and when we simplify, we get 972 plus 160. Combine those like terms and we find out, yep, we really did make $1,132, and so we know the solution is 8132. When you do problems like this, don't forget to add your units. And that's it. Thank you.